Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about exponential functions. Right, so the first thing that I want you to do as part of your work is I want you to evaluate and fill out this table. So we have two functions, y is equal to 1/2 to the x and y is equal to 2 to the x. And I want you to evaluate for the values of x is equal to -4 through x is equal to 6 for both functions. I'm going to pause here. And then let's check your work. Right, so as you fill out the table, you should get these answers. And so what I want you to realize is that as the values for the function y is equal to 1/2 to the x, as the values for x become greater and greater or increase, the value of the function is decreasing to a value that's close to 0. For y is equal to 2 to the x, as the values of x get greater and greater, or move to positive infinity, the value of the function gets greater and greater and approaches infinity. So basically you have one function that's moving from infinity to 0 and one function that's moving from 0 to infinity. And if you were to graph positive infinity, if you were to graph the exponential growth function, so y is equal to 2 to the x, then you're going to look at a function that has an asymptote of y is equal to 0, and then gradually and then quickly increases in value and moves to infinity. So that's the exponential growth function. Y is equal to some value that's greater than 1 to the power of x. And the parent function for an exponential growth function is y is equal to a times b to the x, where a has to be greater than 0 and b is greater than 1. So parent function is similar, and the growth function is similar to y is equal to 2 to the x. That's why I represent it here. In this case, the asymptote is the x-axis, so the graph gets closer and closer and closer to the x-axis, but never touches it as x becomes more and more negative. And the domain is all real numbers. So you can substitute any value in for x and get a real number result out for y. Right, so the exponential decay function is represented by y is equal to 1/2 to the x, where a is still greater than 0, but now b is a value between 1 and 0. So that is represented again by the table that we selected here, y is equal to 1/2 to the x. And this function, I have exponential decay, as you can see, as the values of x become greater and greater. The value for the function decreases and moves towards the value of 0. So we call this an exponential decay function when b is between 0 and 1. So I have a value from infinity. As x becomes greater and greater, that value of that function moves closer and closer to 0. So the asymptote again is the x-axis, and the domain still is the value of all real numbers. Now the range is going to change based on the function. We're going to talk about transformed exponential growth and decay functions in just a moment. So the range will vary, as will the asymptote. But the domain will remain as all real numbers for this function. So you can place any value in for x and still get a real number result out for y in both the exponential growth and decay function. All right, so let's talk about transformed exponential growth and decay functions. And I know there's a lot going on here. So we'll start out with the parent function of a transformed growth and decay function. And so we're going to write that as y is equal to a times b to the x minus h plus k, where h represents the shift of the parent function horizontally by h units. So you have to be careful again. You should have seen this function or this kind of form of the function before with the h and k values. The value of h here, in this case, you have a minus h. So h represents a shift to the right by h units. And the k value represents a shift up when it's a positive k, or down vertically. So let's take an example. Y is equal to 2 times x minus 2 plus 5. And let's relate it to the parent form of the transformed exponential growth and decay function. So a in this case is just 1, it's not stated. B is 2, so this is a growth function. My value for h is not -2, but 2, because I start out with a form of a function of minus h. So this is -2, h is 2, and k is 5. So you can consider changing the sign of this value to represent h and leaving the sign of this value to represent k. So I'm going to shift the graph plus 2 units to the right and 5 units up. So h represents a shift horizontally from the parent function. K represents the shift vertically by k units from the parent function. A represents how the original function is either stretched or compressed. So if a is between 0 and 1, then the function is stretched, meaning that I'm getting to the y values at a slower pace, so to speak, because I'm scaling it by a factor of 1/2. And if a is greater than 1, then the growth function is compressed, meaning I'm getting to the y values more quickly. I'm scaling it by a factor of, in this case, if I were to make this 2, that would be scaling it by a factor of 2. So if it's greater than 1, the function is compressed. If it's between 0 and 1, then the function is stretched. Now, I can also change the sign of the function. We said originally that the value for a had to be greater than 0. Well, let's just say in terms of drawing the graph, if I were to change the sign of a, then I would reflect to negative. Then I would reflect the graph over the x-axis. So this is the relationship of the values and signs of the different parts of the transformed growth and decay function and how they would relate to an original function. So again, h shifts the parent function horizontally, k vertically. A will either stretch or compress the function, and the sign of a will tell you whether the graph is flipped or reflected or not. So what I want you to do is I want you to take a look at these functions, and I want you to tell me whether or not, in relation to a parent function y is equal to a times b to the x minus h plus k, whether that function represents growth or decay, whether it's flipped over the x-axis or not, how it would be translated, and then compressed or stretched based on the value of a. And we'll come back and take a look at the answers. All right, so the first function, b, is between 0 and 1, so it's decay. It is not flipped because the sign of a is positive. It's shifted 3 to the right and then 5 up, and it's neither compressed or stretched because the value here for a is 1. I'm going to go through one more with you, and then you can take a look at the answers for the rest on your own. Again, this is decay, a decay function for number 2. The value for b is between 0 and 1. I'm moving it 2 to the right and 7 up. And because the value for a is greater than 1, I'm compressing the parent function. All right, so we're going to move on. All right, so now you're going to graph y is equal to 1/2 to the x. And then you're going to fill out a table for the same function y is equal to 2 times 1/2 to the x minus 2 plus 5. And we're going to take a look at the table and then rewrite the function as or graphically, and then compare the two functions. So I'm going to pause here for a moment while you fill out the table and then draw the two functions. All right, you should see that from the original function, y is equal to 1/2 to the x, that's the blue graph. And y is equal to 2 times 1/2 to the x minus 2 plus 5 is the red graph as you've filled out the tables. You'll see that the red function, or the red graph, has been compressed. It's also been shifted to the right by 2 and up by 5. So in relating the two graphs together, you see that I have a exponential decay function. As x gets greater and greater, the value for y gets smaller and smaller. You can see that my graph has been compressed because a is greater than 1. You can see that I've shifted the graph 2 units to the right because h is 2, and 5 units up because k is equal to 5. All right, so I just wanted you to relate the actual values and the graphs of the two separate functions so you can see how one has shifted or transformed from one to the next. All right, so exponential growth model, we've gone through this before. Basic growth model is y is equal to a times 1 plus r to the t, where y is the ending amount, a is the initial amount, r is the percent increase as a decimal, and t is typically a number of years, but it can be any time value. So I want you to use this function to evaluate a $10,000 investment earning 8% interest over 12 years. I'm going to pause here for a moment, then we'll go through the answer. Right, so I have $10,000. Again, remember, we need to include this 1 to retain the original value and then add the interest of 8%. Otherwise, we just end up with the interest that we're earning, not the total amount, which is what we want to get at the end of the 12 years. So 10,000 times initial investment times 1 plus 0.08 to the 12th is equal to $25,181.70. All right, so let's take a look at another problem. Apple stock appreciated 40% per year for 4 years. If Apple stock price was $125 in 2008, what was it in 2012? I'm going to pause here while you generate the answer. All right, so 125 is the initial price times 1 plus 0.4 to the fourth. You should end up with a stock price of $480.20. All right, another problem. A house was purchased at $40,000 in 1990, was sold for $100,000 in 2005. What was the annual rate of appreciation in the value of the house? So now we're trying to figure out what the value of R is. We know the ending value, we know the beginning value, and we know the time. So I'm going to pause here for you to figure that out. All right, 100,000 is equal to 40,000 times 1 plus r to the 15th. You're going to divide both sides by 40,000. 2.5 is equal to x to the 15th. Take the 15th root of 2.5, and you'll end up with x is equal to 1.063. Remember, we're finding out what 1 plus r is, so we'll have to subtract the 1 from this value, and we end up with 6.3%. All right, so exponential decay function. Now, the only difference here is that we change the sign. Instead of plus r, it's minus r. So an example here, a car depreciates at a rate of 10% per year. How much will that car be if it's $30,000 initially after 10 years? I'll pause here for you to generate the answer. All right, so we start, y is equal to $30,000, the initial amount outlaid, times 1 minus 0.10 to the 10th, and you should end up with $10,460. All right, so here's a problem for you to work out. I'm going to let you read this on your own for the sake of time, and then I'm going to show you the answer. All right, so the difference is the difference between the two cars is $20,000. You're going to take that $20,000 at 5.5 interest over 45 years, and you'll end up with an amount of $222,531. And this is the equation and the solution. Okay, so now we're going to talk about writing exponential equations. I'm going to give you an example here. You're going to go through two problems. So writing an exponential equation given some set of information. I know that this is just the same as y is equal to a times b to the x. Where f of 0, x is 0, then the function is equal to 3. So what we can learn from this, if the function a times b to the 0 is equal to 3, then I can figure out that a times 1 is equal to 3 because b to the 0 is 1. So a must be equal to 3. And I'm going to use that information to place that into the second equation. 3 times b squared is equal to 12. Solve for b squared and b ends up being equal to 2. So my function is y is equal to 3 times 2 to the x. And f of 4 ends up being equal to 48. So I'm going to give you two classwork problems. I'm going to pause here while you solve them. Okay, I'm going to show you the answers going through the same process, and then I'm going to move on. As you can see, the first one is exponential growth, and the second one is exponential decay. Okay, so now we're going to talk about half-life and doubling or quadrupling in a period. And we're taking the original growth and decay function, and we're rewriting it to model doubling or halving by period. All right, so the half-life model is based off of that formula. A sub t is equal to a sub 0. A of t is equal to a sub 0 times 1/2 to the t over r. And then what we're adding here is the value of r, and r is the half-life time. So I'm going to show you a problem. You're going to work it out, and I'm going to show you the answer. That's going to be all the time that we have for Rotten Math. Please join us again for the next edition.